Bismillahirrahmanirrahim. Good evening. Today we will do something like summary to this article. The article title is Observation of Double Exchange Driving Electron Resistance to the Structure contained from Latanium, calcium, manganite, and 3 atoms of oxygen belong to thin film. Let's start. The overview will be started from abstract and finished with reference, and we will talk about the summary by using summary ideas or simple ideas in abstract and introduction, and after that go ahead to details and experimental details and result, and we will do simple summary to all of this article. Let's start from abstract from this first slide. We will talk about two methods and something like briefly information about them, what the difference between these two ways to measure the resistance. And after that, the most important things will be some images. I take it from this article, and we will try to illustrate all of these together. Now let's start from, like I said before, we have two different ways to measurement the electric resistance in this structure, or we can say that we can use the parent or general structure to the simple lithium, calcium, manganite, and 3 atoms from oxygen, or we can say suddenly La0.67Ca0.33MnO3 configuration. These two ways to measurement the electric resistance. First one in plan configuration. The second one is the out of line configuration. Let's take simple information about all of them. The first one in plan configuration, a shift of material isolator transition toward low temperature. Here we will note we will dealing with low temperature, and we want to talk about when we'll try to illustrate the image, we will understand all of these ideas better. Let me put this arrow here. Yes. With increasing in the current, in the applied current, which is attributed to Joule heating effect. And the second one, like I said before, the out of plan configuration, the material, the metal isolated transition is found to shift toward high temperature. What does mean? That means in a plan configuration, we will dealing in low temperature, and out plan, we will dealing with high temperature for out of plan configuration. Like I said before, this observation agrees well with the predictions of double exchange theory. At the inner plan, we was dealing with the Joule heating effect. In out of a plan configuration, we were dealing with the double exchange theory toward explaining both the magnetic resistance and electric resistance behaviors of manganite by using the double exchange theory. Why? Because we're dealing with out of plan configuration. But in another word, when we're dealing with any plan, we will dealing with low temperature, and at the same time, we will dealing with Joule heating effect. It's an important difference between these two ways to calculate the electric resistance, and we will we will take brief information and important information on all of these in the next slides by using image and something like that. Here, by using the parent simple or the general simple, this structure, this belong to the closal magnetic resistance of materials, possessing interesting spin lattice charge degrees of freedom. This structure belong, like I said before, to CMR, that's mean closal magnetic resistance, and at the same time be processing with the three important things. These are the charge degrees of freedom, lattice, intrinsic spin, lattice, and the charge degrees of freedom. Let's take briefly about idea about what is the charge degrees of freedom. Actually, I didn't know, but I did simple research in Google. We can summary a charge degree of freedom by these few words. It's a number of direction in which a particle can move freely. A number of direction in which a particle can move freely. Or the total, or we can say, we can use another word, or the total number of coordinates required to describe completely the position and configuration of the systems. That's mean it's focused in two important corners. The first one is the position. The second one is the configuration. The position and the configuration, the charge free degrees focused on all of these. Now, the material exhibits both the ferromagnetic material and charge ordering isolating states, dependent on what? Actually, dependent on the calcium concentration in this structure. For calcium concentration between 0.2 until 0.5, let's see what we'll do. We note is the ferromagnetic material state was observed below the transition temperature. Below the transition temperature. I'm talking about the ferromagnetic material. And at the same time, the ferromagnetic material state is well explained by double exchange theory when calcium concentration equal between 0.2 until 0.5. The observed below the transition temperature, and we will still dealing with the double exchange theory when calcium equal 0.2 until 0.5. The exchange of the EG, like I said before, that's this two letters illustrate to us the low level of any atoms, anything has few shields, has or have many electrons, like we learned in chemical course. Few shells, depending on how much this material has of electrons, 2, 8, something like that, keep going continuously. And now I'm talking about the first one. This contains from 3 lines or 3 shells, like we know. This EG electrons between these two different ions, Mn3 plus and Mn4 plus ion, results in enhanced conductivity. This support the conductivity characteristic in this material. Okay. Now we come back to our structure. The author used and worked on the structure, and after that started to write all of this information. Here, LCMO exhibits a large closal magnetic resistance effect with the magnetic resistance reaching as high as this important and interesting results, because it's a huge results, 100%, equal 127,000 100% with applied field of 6 Tesla. I'm talking about the magnetic field equal 6 Tesla. Here we're dealing with a huge number. Like I said before, this structure accepts a large closed magnetic resistance, effect with some relation with the magnetic resistance. Reaching what? Reaching a high resistance equal approximately 127,100% with applied field for 6 Tesla. This interesting number to any physicist. The electron resistance in manganites was reported on charge ordering state at certain levels of doping concentration, not at any levels, but at certain levels of doping concentration. Here, when we say X equal 0.3 until 0.33, the closal electrical resistance and closal magnetic resistance phenomena have the same, the origin and effects. That's mean here this critical result of X equal 0.3 and 0.33. The magnetic, the closal electric magnetic and closal magnetic resistance, closal electrical resistance and closal magnetic resistance will share two characteristics. These are the origin and effects. The double exchange theory predicts that the material isolator transition should shift to bigger temperature, because the double exchange theory supports that. With increasing current, the double exchange theory predicts that the material isolator temperature should be higher value, higher result of degree of, sure we're talking about Kelvin and all of these results when I'm talking about the temperature, and when we start to explain the information about the next image, everything related to the temperature here, we will talking about it by using the Kelvin unit. And at the same time, with the increasing in the current, that means the temperature will go to increase when the current increase, because the double exchange theory supports this form. The electric resistance measurement in ferromagnetic material state magnets should shift of material isolated temperature toward lower than temperature. That means some difference between the double exchange theory support the temperature to be bigger, to be higher, to start to grow, but electric resistance support to make the resistance go toward the smaller results with increasing, sure, the current. In this report, the experimental technique to study the electron resistance of this constructor thin film using in plan and out plan measure configuration to can determine the electrical resistance, like I said before. Now, the out of plan electron resistance measurements follow the predictions of double exchange theory of manganese, like I said before, and in the plan electric resistance measurement, the gel heating. The thin film was characterized by using the X-ray diffraction and ferroelectric scanning electron method techniques. To obtain film is found to be of single-phase polycrystalline nature, and the calculated lattice parameter equal approximately 3.86 angstrom. The ferroelectron scanning electric field magnetic image of this film indicates the presence of well-connected grains whose size varies between here. We have important thing, the grains will be from 20 nanometer and until 200 nanometer in the field effects scanning electron magnetic. We'll start the grain from 20 nanometer until 200 nanometer. The resistance of the simple LCM, or we can say it's shorter, it's a simple, illustrate to us the simple, we work on it. Thin film was measured by varying the temperature from 15 temperature until 300 Kelvin. We dealing with a curve of temperature starts from 15 until 300 Kelvin. The different values of applied current in plane and out of plane configuration with different value. That's mean, like I say, I will say in the next slides, we will focus on the image, and after that we will take the IV curve individually and talk about it. Here, we keep going to deeply information. Here, this image illustrates to us the both of these methods in a plan with positively, negatively terminals, and here at the same time with out of a plan. And here this our structure. Below the silicon, here the silver from all of these terminals. The schematic of simple with contacts used for measuring the electrical resistance on this structure, thin film in plan and out plan configuration using two probe method is shown in figure number 1, like I said before. The specific contact resistance of the silver AG paint contact measured using the transition line method. Using here transition line method. The resistance here equal approximately 8.8 plus negative 1.5 ohm centimeter square, where at 300 Kelvin. At figure number 2, like we're seeing here, we have two important sites, the temperature at Kelvin at x-axis and the resistance at kilo ohm unit at the y-axis. And now we will know the relation between all of them in this curve, or what this curve illustrates to us. Here shows the variation of resistance with respect to temperature for fixed value of applied current. That's mean here we study the relation between the resistance with respect value of temperature with specific applied current. That's mean here at black one is the current apply is 0.1 milliampere. At the red curve equal 1 milliampere, and keep going like that. Like we're seeing here at 0.1, actually we will focus on this and the next side. Here we have two sides. This peak or this top point, all of these curves. The first one starts from low point until this top. We will ignore it and focus on until this top. Okay. Here we will note something when we increase the current, the resistance will decrease. For example, at block 1 equal 0.1 milliampere, the top, the maximum value at this top of this curve will equal, for example, here equal 11 kilo ohm, but at the blue one will equal approximately 7, that's kilo ohm. That's mean here we note decreasing the resistance with increasing in the current. Here, like I said before, and below the 50 Kelvin, what we'll do? The curve will act like, these curves will act like a line, and at the same time, we will know some similarity about values with the first start point at all of these curves, some similarity, approximately equal each other. To the grain boundary, tunneling similar to the observed for polycrystalline manganites. Here, let's take a look about the IV curve. The IV characteristics of this structure, thin film measured in a plan here in a plan configuration at different temperature, will act some like lines here, from minus results to positive results, some line at the red, at the yellow, at the blue, and all of that continuously like that. The curves are found to be linear. What does mean when I see linear behavior? That's mean I'm talking about ohmic contact. Now let's take a look about the peak temperature and the peak resistance. What does mean peak? Peak does mean the maximum, something like that. At figure 2b, as well as the peak resistance with will decrease with increase applied of current. Let's take a look what that's mean and let's prove it. Here we have two x-axis at the current applied current, start from 0 until 7. And at y-axis, the peak temperature starts from 0 until 220 Kelvin, sure. Here, when I start to, let's talk at first about the peak temperature, the red line. When I start from 0, will be approximately equal 220. After that, at 1, approximately the same result. Until after that, at 3 milliampere, we will note a huge decrease from 1 to 3 milliampere, from 220 Kelvin to approximately 207 Kelvin. That's mean what? That's mean when we increase the resistance, the peak temperature is increased. Now let's talk about the peak resistance with applied current here. Or we can image this on the another side, okay? Doesn't matter. Let's take a look about when we increase the current, what we'll do about the peak resistance. At 0, equal approximately 11. At 2, equal less than 11. At 3, equal 10. What does mean? That mean decreasing. The peak resistance is decreasing with increasing the current. Here, variation of metal isolate transition temperature and peak resistance with applied current. We note what? We note all of the peak temperature and peak resistance decreasing with increasing the current at in configuration, not out until now. We're talking just about the in configuration in method to calculate the electric resistance. Now, experimental details, the shift of peak temperature towards low in configuration method is attributed to Joule heating effect of the sample, which becomes large applied current. Here in configuration, we're dealing with low temperature. I repeated that again, and with Joule heating effect. And however, the shift of peak temperature towards lower temperature cannot be explained by double exchange theory. We will dealing with double exchange theory with out configuration method, where the spin polarization induces the shift of peak temperature toward high temperature. Here we have something like condition, where the spin polarization induces the shift of peak temperature towards higher temperature. Here, let's start to talk about the second method to calculate electric resistance. In out of applying configuration, at this figure, figure 3a, we see something, the temperature at the x-axis and the resistance in kilo ohm at the y-axis. And let's start to explain the curves, all of these currents, and what that mean each color from all of them. Shows the resistance measurement different with different applied currents, because here we will start to apply current equal at first 0.5 microampere, and at the last until 1000 microampere. That's mean many values of applied current. Here in out of applying configuration, different applied current, like I said before, start from 0.5 microampere until 1000 microampere, where silicon substrate itself serves as an electrode. The resistance will decrease with increase the current. Let's take a look how. For example, the clearer one, in my opinion, is the below equal for when we applied 4 microampere. 4 microampere will approximately equal 337 kilo ohm, and at the red one or green one at 2 microampere equal approximately 32 kilo ohm or 32.5 kilo ohm. That's mean what? That's mean decreasing the resistance with increasing the current. The current increasing, the resistance decreasing. They find the peak temperature shifts towards high temperature with currents. Now let's talk about what that's mean. These few words, what that's mean. Like I said before, peak, that's mean the maximum value, the maximum point, peak temperature will be to all of these. Here, the author said the peak temperature, the peak value of this transition point or whatever will be at higher temperature, not in the lower temperature. And let me prove that, like we're seeing here. Here 250 Kelvin, and here this peak temperature between 250 Kelvin until 150 Kelvin. That's mean at high temperature than 50, 40 temperature. Now, let's talk about that. Figure 3b shows the peak temperature increasing sharply, but when and where? For lower currents here, start from 0 microampere until we can say less than or approximately 50 microampere at this spherical. Will be then increasing will be sharply, and the increasing will start keep going, but with some change, and arise gradually from sharply exponentially to gradually step by step for higher currents. After 50 at higher at higher currents here, start from here and keep going to draw something like this curve. At low current here, with low current here, with high current here inside this spherical. The peak resistance is gradually decrease with increase the current here. The peak resistance at kilo ohm decrease with increasing the resistance. Let's take a look how and why. At 0 microampere will be more than 220, and keep going at 300 microampere will equal less than 240, and keep going until 1000 microampere will equal less than 208. Less than at 1000 microampere equal less than 30 kilo ohm. Yes, here at 0 microampere equal approximately more than 38. At 300 microampere equal approximately more than 34, and at last at 1000 microampere equal less than 30 kilo ohm. That's right. The peak temperature shift to high temperature with high applied current is northerly. This negative electron resistance effect is similar to typical magnetic resistance observed in manganites. So for such electric resistance behaviors of manganites is not reported. Most of other measurements show the shift of peak temperature towards low temperatures. It's important. Important notes in this slide start from this. Most of other measurements show the shift to peak temperature toward lower temperature, where simple heating with Joule effect results in incorrect electric resistance behavior of manganites. Here, let's take a look about the IV curve and out method, out of a plan configuration, indicates that the current voltage curves are nearly symmetric with a slight non-linearly. Here, because this behavior, it's different from in a plan configuration. Here it's not linearly at all. That means we're not dealing with ohmic low ohmic contact. The electric resistance effects observed in out-of-plane configuration can easily find a direct correlation with double exchange theory. Some easy relation between the electric resistance effect in out-of-plane configuration easily find a direct correlation in out-of-plane configuration with a double exchange theory, which is used to explain the magnetic resistance in manganites. Now the shift of the peak temperature toward high temperature and the reduction in peak resistance array due to the strong interaction that occur between the carrier spins and localized spins of manganese ions. And the double exchange theory describes what? Describes the ferromagnetic coupling. The double exchange theory in out-plane configuration describes to us the ferromagnetic coupling between manganese ions brought about by the low level of electrons at EG, which make spins oriented when jump from Mn side to another. That's mean from Mn 3 plus to 4 plus and from 4 plus to 3 plus. Between the manganese ions is brought by the level electrons, Eg, which makes the spin oriented when jump, the spin oriented specifically when jump from Mn to another. When the applied current is increased, what will do? The Eg electrons are forced to move forward irrespective of orientation. Irrespective of orientation, the Eg is forced to go toward irrespective of orientation, Mn ions when the current is increased. The ordering of manganese ions results in decrease of resistance and shift the metal isolated transist. Yes, we can say transist towards high temperature, similar to that observed in manganite resistance. The ordering of manganese ions results decreases will be lower of resistance and shifts, turns the metallic isolated transition towards high temperature, keep going to high temperature. But let's make it what? To make it similar from what? Make it similar to the observed in magnetic resistance. Some relation between electric resistance and magnetic resistance, some similarity, and we try to discuss a different situation at high temperature, low temperature. The current density, now we're talking about another element, G, it's the current density in the out of plan configuration and in the plan of configuration, and we'll try to do comparison between them. The current density J in out of plan configuration equal approximately 0.1 angstrom divided on square centimeter at specific current here equal 1 milliampere is found to be about 3 orders more than 3 times more than the magnitude lower than the observed, lower than 3 times lower than observed of any plan. That's mean the density, the current density in out of plan configuration is lower than 3 times of in a plan configuration. And the density in a plan equal approximately 77 angstrom divided on centimeter square to the same current applied. The Joule heating effect is 3 orders less of out of a plan configuration, because in out of a plan configuration, we're dealing with another theory. Like I said at the first slides, the Joule heating effect we will notice at the in-plan configuration. This leads to what? This leads to a higher value of electric field for out of a plan configuration when compared with the in-plan configuration. That's mean because that we will note higher value in out of a plan more than the value of electric field in the in-plan, which is sufficient enough for ordering of manganite spins. Now, let's talk about another thing in the in-plan configuration. In in-plan configuration, larger value of current results is a smaller electric field, which is not sufficient to drive the ordering. Why not sufficient and can't drive the ordering? Because the electric field is not enough. It's not a large value. Now the Joule heating increasing due to the large current. Note, our simple film shows symmetric electric current voltage curves and nearly same the peak temperature shifts for both the positive and negative currents in out of a plan configuration. In out of a plan configuration, some similarity about positive and negative currents and out of a plan configuration. And in AV curves. Here, the results. These studies shows that the exact mechanism responsible for the electric resistance phenomena in manganites is still not clear and remains to be understood. To overcome this issue, short current pulse were used in electric resistance measurements, and the results thus obtained is found to agree with the predictions made by the double exchange theory to some extent in the electric resistance measurements when we're talking about short currents and electric resistance measurements by using the double exchange theory. By using simple a measurement configuration, we could demonstrate the electric resistance directly correlating with the magnetic resistance. Correlated with the magnetic resistance. I'm talking about the electron resistance when this measurement configuration could demonstrate the electric resistance directly with magnetic resistance of manganite by using this article, by using and benefit from all of these information in this article, by focus on this work results from working from the structure, not symbol. Now we have observed slightly larger value of resistance for out of plan configuration compared with the in plan configuration. The resistance in out plan is more than in in plan. The resistance calculated for the out plan configuration found to be about 7 orders. We support this idea. 7 orders of manganites bigger than in the plan configuration. And the simple heating due to Joule effect is not seen in resistance measurement in out of a plan configuration for the range of currents. The range of current we used the measurement in out of plan about the Joule effect is not seen in these values of current applied. I'm talking about because the Joule effect is not clear, is not seen in resistance measurement in out of a plan. Out of a plan resistance of this manganite indicates the major rule indicated by the out of a plan resistance manganite and a plate interface with this structure. The same temperature range for in plan and out plan configuration with peak temperature is nearly the same out clear the material isolating transition observed. We have measured now I'm talking about the last slide. The last slide is the summary. We have measured the variation of resistance with temperature in the simple thin film in two different configurations, like I said, in plan and out plan. And how the first image illustrated to us the outer shape to this mechanism, outer shape to this device for a fixed value of applied currents. The measurement of electric resistance and the out of a plan configuration, more advantages, more benefits to us from the in plan configuration. And out of a plan configuration, the peak temperature increases with the applied current. In addition to decreasing resistance, the mechanism responsible for electric resistance is similar to that of magnetic resistance of manganite. Some similarity, like I said before, between the electric resistance mechanisms and magnetic resistance mechanisms in manganite. That's it. Thank you about your watching, your listening. I wish it was helpful. Thank you so much. See you in the next lecture.